Good morning, students. Sorry for late connection. Okay, because of some internet problems. Let's start today's discussion. In the last few lectures, we have been discussing about the BJTs and then its different configurations which we can do. Okay, so these different configurations will be dealt in detail in the coming semesters. Okay, so only here we were having the DC analysis of such simple circuits of the transistors and their design criteria. So hope you have been doing well, okay, in solving the problems based on these BGTs. Today we shall start with FETs. FETs are commonly known as these are actually field effect transistors and little different as compared to the BJTs. We shall also compare the BJTs with the FETs, but these are the different type of transistors, okay, based on different phenomena, one can say. So these are different types. First is junction field effect transistor, another is MOSFET, metal oxide semiconductor, FET. Again, these MOSFETs are generally of two types. One is called as depletion MOSFET, D MOSFET, and another is enhancement MOSFET or E MOSFET. So we shall investigate one by one these FETs. So we shall first let's see uh, the FETs and BJTs similarities and differences. Similarities, we can say that FETs and BJTs both can be used as amplifiers, can be used as switching devices, can be used as impedance matching circuits. So based on their uses, we can say that they are similar, but there are salient differences between these FETs and BJTs. The FETs are something called as voltage control devices, whereas BJTs are current control devices. So in the BJTs, we have already discussed that we have seen that we can change the current based on the input current IB, base current, okay, or we can also change the IC by changing the IE. So we have seen that here mainly we talk about the currents. So the output current, that is IC, can be either changed by IB or IE both. Okay, so these BJTs are essentially the current control devices. Whereas we will discuss in detail now that FETs are voltage control devices, and we shall also understand the working of the same. The FETs have higher input impedance, whereas BJTs have higher gain. So higher gain means this is a gain, maybe the voltage gain or the current gain. These are quite high for the BJTs, whereas FETs have higher input impedance. If we look at the only input impedance comparison, then we can see what BJT is, that this input junction, okay, the input where we apply between base and emitter, say this is mostly this is forward biased, and we have understand that forward bias the junction gives a smaller resistance, okay. So that's why this gives a smaller input impedance, okay. So BJTs have higher gain, and these have also lower input impedance. But it is not true for all the configurations. There are a few configurations which of BJTs also which can give quite higher input impedance. But if we compare that impedance with the FETs, then it will be even now smaller. So we will see that why it is so, why this is giving high input impedance. Okay, we shall also investigate why how this is voltage control device. Another thing is here FETs are less sensitive to temperature variations and are better suited for integrated circuits. So integrated circuits, we know little bit about that these are the transistor circuits made on a single substrate, silicon substrate. Okay, so on a single substrate we put all our transistor circuitry to perform certain job like amplification or some any other controlling phenomena. So integrated circuits are those. So now integrated circuits are having say millions of transistors. FETs are generally more static sensitive than BJTs. We will also see these points in detail. So to start, let us look at what the FET looks like. So to start here, similar to the BJTs, which were of two types like NPN transistor and PNP transistor. We also have there two types of FETs, junction field effect transistors. One is called N channel, another is called SP channel. Okay, so here and the cross sectional view of N channel JFET is given here. So this is essentially the N channel JFET. So if we look at the cross section here, then we can see that there is something called as N channel here. There are between two regions. Okay, these drain and source, these are similar to the collector and emitter of the BJT, and the gate here which we have is similar to that of the base of the BJT. So function is almost similar, but construction if we look at, that is quite different. So what difference one can notice is this one. First thing, that in the BJT we were having this kind of cross section like PNP, and we were using this middle section as base, and one section was used as emitter and another was used as collector. Okay, so the basic difference one can see is that now the base which was there in the middle for the BJT, this is for BJT here. Now this section is used to conduct the current through between across it. Okay, and the controlling is done by these two end-to-end same regions. Okay, so that is the basic difference here from the construction point of view. To discuss little more here, let us draw the cross section of this FET here. So we start with BCS, say N type of semiconductor. We may make two regions here inside it of opposite doped. that is P type. Actually, these are heavily doped regions, so we will put a plus here also. P plus means heavily doped P type. Okay. So let us first understand the construction here and working then later. These end-to-end points are connected, contacted here. Okay, not connected. These are contacted with a different regions here. One is called as drain, another is called source. So we can see here that either this can be called as source or and this can be called as drain also, because it seems quite symmetric here. Okay, either a contact can be called as drain or source, and these two ends are connected together to declare as gate here. Okay. So one can have, say, one substrate kind of thing like this here, and into this one can etch some regions here from both sides. It is not able to be shown here inside this, and these regions are, say, dot by P type, and this is N type. So one side is okay, drain source, and these other regions are connected together like this to have the gate. So three-dimensional view, maybe just observe something like this here, and two-dimensional view can be thought of this type. Okay. So this is how this looks like here. So once we have these regions created, as soon as these are created here, these are P plus regions, we can see that there is a depletion region also created. Okay, so we know that as soon as we put two different type of materials together, then there will be a depletion region created here across this. So say this is the depletion region. So depletion region is similar to that of the PN junction here. The heavily doped region will have little penetration of the depletion region into it, and the lightly doped region will have larger part of the depletion region into it. If we forward bias this, then this is no different than the simple diode in the forward bias. Okay, and a current will flow through it. Whereas if we reverse bias this, then there is no current possible. Okay, only the reverse saturation current may be possible. No other current will flow through it. Okay, so this reverse saturation current is quite small in magnitude and we can neglect. So in the reverse bias condition, we can say that this offers a very large impedance. Okay, so that is the situation here at the gate. So P plus N junctions here at the gate, these are reverse biased. Okay, these are reverse biased. That's why it doesn't conduct any current through it, except the reverse saturation current I naught. Okay, and because of the reverse bias, this P plus N junction, this gives a very large impedance. Before further details here, let us have overview of this. So this JFET is having three terminals, namely drain, source, and gate. Drain and source are connected to this N channel from both ends, and gate is connected to the P type of material over here for N channel. If we are talking about the P channel, then this P channel will be made of P type of material here, and we will have the doping of opposite materials N plus regions here, and the N plus regions connected together. These will form the gate, and this both ends of this P type of material may be called as drain source respectively. So this is P channel here. This is P channel FPT, whereas the former was N channel FET. So if we look at I was lost with connections. Again, it is I think connected. So the basic idea about the JFET operation, okay, we were trying to discuss about here. So the exercise is like we can compare this as water tap, and in the water tap we can say that on one side we have a source of water, and there is a drainage of water on the other side, and we can control the flow of water through it by this gate here, tap. So okay, the working is quite similar to this here. So in our FET also we can make the charge flow across drain and source, and that can be controlled with the help of this middle section called as gate. So gate is here. So if we apply some voltage here, we can modulate the channel width through which this uh, charge is going to flow across this drain and source, similar to that water flowing through this water type. So the cross-sectional area through which the water is flowing, we can control by the knob here. So this knob can be just tightened to reduce the area or increase the area through which the water is flowing between the source and drain. So the action is quite similar. So this is only for understanding purpose. So let us try to understand the working of this JFET. So depending on voltage applied, we have three basic operating conditions for JFET. The first is when we don't apply any gate biasing voltage, then what happens? And when we apply a voltage such that the gate junction, okay, that is reverse biased. So suppose this is P channel, sorry, let us say this is N channel and this is P plus regions here. Okay. So if we don't apply any gate voltage, the source voltage and gate voltage, both are say grounded here, such that VGS is equal to 0, then we can see what happens to the P plus N junction which is formed here. So the junction formed across this P plus N region here is similar to that which is the case for the unbiased PN junction. So we don't apply any voltage across this. So there is some inbuilt potential barrier. There is a depletion region which prevents the flow of the charge carriers across it. Okay. So that is the condition over here. Now under such a situation, if one applies a voltage difference across this N channel, which we call as drain and source now, as already discussed, then this will establish some external field. The positive polarity of this battery will establish positive voltage on the drain side and negative on the source side, and we will see an electric field across this region as shown here. Okay, from drain side to the source side. So in the N channel, the electrons will accelerate under this electric field and will start moving from source side to the drain side, opposite direction to the electric field established. Okay, so the electrons here will start flowing from source side to the drain side, but the current is going to flow from the drain to the source side, because the current flow direction is that of the positive charges. Electron is flowing from source to drain means positive charges are flowing from drain to source. So current is flowing from drain to source, whereas electrons flow from the source to drain. So that's what happens here. So when VGS is equal to 0, we don't apply any biasing voltage at gate PN junction here, then it gives the maximum possible cross-sectional area through which the current is passing. Okay. So this current which we get is the maximum current. Okay. One thing before proceeding, can we apply a BGS greater than 0? If we apply a BGS greater than 0, then what will happen to this P plus N junction? This P plus N junction will become forward biased. Okay. And a huge current will start flowing through this gate here in this condition. So in this condition, we will see a current to flow in this direction. Okay. So between this, the current will start flowing. So that is undesirable here. We want only gate to control. We don't want a large current to flow through this, as was in the case of the BJT also. We didn't try to apply use this input terminal to consume more current. Okay, so input should consume as small current as possible. Why it is desired? Why this input should have a small current? We know that we use some source voltage here. Okay, which may be in the amplification cases, we may need the input signal to be amplified. Okay, these input signals which are generally applied here of small magnitude. These are small magnitude. These are not very large. Just like suppose we want to amplify some signals received from the microphone. So microphone, okay, is just a kind of actuator which responses according to the voice. So its output may be of the order of say few microvolts, or at most it could be say millivolts, not more than that. Okay, so a fraction of millivolts. Okay, not millivolts. So that is very small signal, and such a signal has to be amplified. So if we draw large current to from this, then it will make some loading effects on the input signal. Okay, so avoid loading. Okay, to avoid loading, we must have this current to be very small, also drawn from the source. And for that reason, we don't want to extract more current from the input source, from the input terminal. Okay, so that is the reason we insist that a small current should be taken from the source. Okay, so we cannot forward bias this. So we cannot apply a voltage greater than 0 BGS. Okay, for the N channel. For the P channel, it will be just opposite. Okay, for P channel, we don't apply a voltage BGS less than 0, because in that case we will have N plus P junction, and to bias this to reverse bias this, we must apply a positive gate voltage. Okay, okay, so that's what it is. We cannot apply a negative gate voltage there, just like for P plus N junction. In this case, for N channel, we cannot apply a positive gate voltage. So only we can apply this BGS less than 0. Now, if suppose we apply a BGS less than 0 for N channel and BGS greater than 0 for P channel, then it is going to be reverse bias. If it is reverse bias, it means the depletion region going to extend here. Depletion region will extend more into the channel. Okay. So, what we can see that if we apply a reverse bias voltage at gate, okay, then the depletion region is going to extend more and more into the channel, because this is the gate region is heavily doped. Something like this it may happen. So if we apply a larger gate voltage like this here, if BGS reverse biasing voltage is increased, then this depletion region will also increase more and more into the channel. So what we see here, due to this increase in the depletion region, the effective cross section through which the current flows get reduced. Okay, so that's how the water tap knob kind of thing action is taking place here. If we apply more and more negative gate biasing voltage, so that it is reverse more and more reverse biased, so the cross-sectional effective cross-sectional area decreases through which the charge was flowing. Okay, so charge flows through a small cross-sectional area and thereby the current decreases. Okay, so that's how we can decrease the current, but we cannot increase the current. Why we cannot increase the current? The maximum current, we have already said that it is for BGS is equal to 0 when it is not biased. Okay, so for this case we have maximum current, and if we increase BGS, then the current is going to decrease. Okay, so we can only decrease the current in such a case. If we increase BGS more and more, okay, let us say BGS is increased more and more, then we shall see that the current is also current is going to decrease more and more, like this. If we keep on doing so, then there will be a BGS for which we will have the effective channel area to become 0. Okay, so if effective channel area becomes 0, then and there will be no current possible. Okay, whatever the BDS we apply, okay, now in this case whatever the BDS we apply, we cannot make the current to flow across this drain source. This particular value of the BGS is called as BGS off. Okay, so there exists a gate to source voltage negative, okay, gate to source voltage here, which may effectively make the channel to disappear by extending more and more depletion region into the channel, and it can make the current to become zero for whatever the BDS we apply, because there is no channel to exist. So this is one thing just we try to look at. So we just see here that uh, we can make the FET to operate when we have BGS to be equal to 0, and BGS is such that it is reverse biasing the gate to channel PN junction. Another thing we can see here, that when we take the BGS is equal to 0, we don't apply any voltage across gate and source. Let us say that. So it is essentially by connected here, gate and source is connected together and to the ground. So BGS is equal to 0 here. Now in this case, if suppose we apply some voltage across drain to source and vary it, then let us investigate what happens. So there is very interesting thing happening here. For a particular value of BDS, we will have a channel like this here. Okay. So we have, say, this P plus region N channel, and we are applying a BDS across it. This is actually connected to 0 gate. Gates are connected to 0. Like this. So for a particular value of BDS, we will start flowing the current. For small values, so suppose we start with a small value of BDS. As we increase BDS, then what we can see that this particular N channel region, okay, which is semiconductor, this is semiconductor and also lightly doped. Okay, as we can see. So this gives a significant amount of resistance. Okay, because of this, we have significant amount of resistance. So significant amount of resistance means here across this drain and source, we see this resistance. So this resistance is actually not located at a single point, but rather it is distributed throughout this channel. Okay. Actually, we can assume we can take some in particular small thick stripe here, and we can say that every stripe is going to give some amount of resistance like this. Okay, and through this we can see that the current is going to flow. The same amount of the current is going to flow. Okay, due to this BDS applied, we have already said that the charge carriers start flow and they will form the current. The same amount of current is going to flow through all the sections coming the series. So these will make some voltage drop here. Okay. So voltage drops will be, say, due to this voltage drops, these different section points can be said to have different voltages here, and these voltages can be found by voltage divider rule. Okay, so if we use voltage divider rule, then we will see that the point closer to the source, that is going to have least potential. So in this case, B1 is less than B2, is less than B3, is less than B4, is less than B5, is less than B6. The minimum value is going to be that of the source, which is at zero potential, and the maximum value is going to be equal to BDD of drain. So drain is having the maximum, this say, let us call B, I think in the figure we have called this as BDD. Okay. So BDS is nothing but BDD minus 0. That is BDD for this case. Okay. So here the minimum value of minimum voltage is that of the source, and maximum voltage is that of the drain, BDD, and all other are in between. Now gate is at ground potential, at zero potential. So we can see the relative potentials of this P plus N junction. Suppose we look at the relative potential of these regions, then it happens to be different in different cross-section areas of this P plus N junction. So the drain is having higher potential and source side is having lower potential. So reverse biasing on the source side is less, whereas the reverse biasing on the drain side is more. Due to this similarity here, we expect more reverse biasing happening on the drain side as compared to the source side. Something like this. Okay. So we see more depletion region on the drain side as compared to the source side. Now, if we increase this BDS, if BDS is increased more and more, then the current will increase more and more, and this effect will lead a more difference in these potentials B1, B2, B3, B4, and we will see that because drain side is at higher potential, so it will getting extended more and more on the drain side. There may exist a BDS, okay, a BDS exists for which the depletion regions of the both sides will start touching almost each other. Okay. So if the BDS, okay, for this BDS, the depletion regions of both sides start touching each other, then we will see that it looks like the current is going to become zero. Okay. But it is not like that here in this case, because as soon as the current tries to become zero, there will be no voltage drops across this channel region, and there will be no more reverse biasing, and no such criteria will exist. Okay. So what happens, it has been seen practically also, that the current doesn't comes down to zero, but it instead becomes constant, because under such a situation there exists a small aperture through which the charge carriers flow, and there is no more decrease in the cross section area beyond that. Okay. So that particular BDS, okay, for which the current becomes almost constant, that is called as pinch off voltage, PP. Okay, this particular voltage is called as pinch off voltage. And in this situation, there exists a small current. So we stop here with this. We will continue our discussion from here in the next lecture. I think time is also over. So you will be going for the next class. We shall stop here. You can look at the more theory of this from the books, and we can discuss if there is some confusion, okay, or in any query, we can discuss in the next lecture. With this, we stop here.